Okay, let's do more 5.3, possibly finish, we'll see. So determinant theorems and Cramer's rule. So how determinants apply, some of the rules of determinants, you can read through them as they apply, and Cramer's rule, which is for solving systems of equations using matrices. One thing to note, if two rows or columns are switched to a matrix, it switches the sign of the determinant. If two rows or columns of matrix A are identical, then the matrix's determinant is 0. And adding multiples of a row or column to an existing row or column doesn't change the determinant. And if matrix A is triangular, that means you have a triangle of zeros above or below the diagonal. The product of the diagonals is the determinant of A. More importantly, what we're going to use in this class is Cramer's rule. Cramer's rule talks about the solution to any system of equations can be determined by cleverly using matrices. So if we just walk through this, ax plus by equals c, and then a second ax plus by equals c, where the a's, b's, and c's are different, can be turned into a function by multiplying by a certain number. Here we multiply by b2 and negative b2 just to make sure that the y terms will cancel by elimination, giving us this term. And we factor out the x and divide. And when you get that, you get this term, b2c1 minus b1c2 over a1b2 minus a2b1. Now what somebody noticed is that this is the determinant. Each of the numerator and the denominator are both determinants to matrices. One is the BC matrix. The other one is the AB matrix. And the coefficients just slot in, because of course the coefficients have an effect on the solution to a system of equations. Now it's impressive that anyone ever saw this, but they did. Now, since we are solving for x, the x value coefficients are replaced by the answer coefficients. So notice that x was equal to, a was replaced by c, but c is the answer. So you replace the x column with the solutions column, and you find the determinant there, and divide it by the determinant of the regular coefficients. This will just be easier to see when we actually do one. And it extends to 3 by 3s as well. It's just a lot of different determinants. So let's just see how this works. Use Cramer's rule to solve this following system of equations. Okay, so we've got dx and dy, and then our denominator one. So dx is the determinant with x replaced by the solution coefficient. So that means the negative 1 and 1 go in for the 5 and 6 for x, and 7 and 8 go in for your y coefficients. dy, the same thing, but you're replacing the y values with negative 1 and 1. And then your denominator coefficient is just your regular set, so 5, 6, 7, 8. So let's see what happens here. We find these determinants. Here we have negative 8 minus positive 7. Here we've got 5 minus negative 6. And here we've got 40 minus 42 by using our diagonals from the last video. This is negative 15. This is 11. And this is negative 2. So what they're saying is that the solution for x is the x determinant divided by our denominator determinant. So in this case, that's negative 15 over negative 2, which is going to be positive 15 halves. It doesn't reduce. Y is the same thing, dy over d. So that's 11 over negative 2, or negative 11 halves. That means our solution is just our xy coordinate. 15 halves, negative 11 halves, like that. So it uses determinants to get solutions. Of course, it's easier said than done. If we wanted to find all three in a 3 by 3 matrix, I have to have dx, dy, dz, and the denominator matrix. Okay, so dx, again, our solutions replace the column coefficients for x, so negative 2, negative 5, 4, 1, negative 1, negative 2, negative 1, 1, 3. And I'm only going to do solving for the x variable in this problem, because you can see it's going to be longer and tedious. So we only really need, remember that x is dx over d. So we only need the dx and the denominator, which is the regular coefficients. The determinant of these two things. So of course, we talked about the determinant of 3 by 3s. You write in the extra columns. We do the diagonals. We add the left to right diagonals, subtract the right to left. So our left to right ones, -2, -1, 3, that's 6, plus 1 times 1 times 4 is 4. -1 times -5 times -2 is -10, so this thing is 0. Left to right, or right to left, going down this way. We've got -1 times -1 times 4 is 4. -2 times -2 times 1 is 4. 1 times -5 times 3 is -15, so this is -7. So that means dx is 0 minus -7, which is 7. We do the same thing for the denominator. Again, write in the extra column, 1, 2, 1, 1, -1, -2. Do the same thing. Top left to bottom right, diagonals. 1 times -1 times 3 is -3. 1, 1, 1 is 1. -1, -2 times 2 is 4. So adds up to 2. Going the top right to bottom left. -1 times -1 times 1 is 1. 1 times 1 times -2 is -2. 1 times 2 times 3 is 6. That's a total of 5. So we have d is 2 minus 5, which is -3. So what do we do with those two things? X equals dx divided by d, which we know is 7 divided by -3, which is -7/3. And we would repeat for the y and z coordinates, and again divide them by the denominator value. The hardest part about this is one little even copying mistake or slight arithmetic mistake can throw off all of your answers, which can be really frustrating. So my suggestion to you is, if you want to check your answers, if something goes wrong, use your normal techniques for solving these. And then, so once you know what you're supposed to get, then you can check back with your matrices to see where something is going wrong. But that's really all for 5.3. This is, again, the last section for test 3. So this next week, we'll go over the stuff, review, and the test will be the following week. And I will see you guys this week.